So in this video, we're going to be introduced to polynomials for our new unit on polynomial functions. And so let's go ahead and get started with this. I'm going to talk about Jimmy's bank account first. And so when Jimmy was 10 years old, he found out that he had a rich uncle who gave him a gift of $1,000 that Jimmy put in his bank account. And so Jimmy put all of that $1,000 in his savings account to save it for college. And so when Jimmy turned 11, he had some extra money. That $1,000, we could think of it this way. If you put that $1,000 in your account and it makes 4% interest, you can multiply it times 1.04 to figure out how much money you're going to have after 1 year. If you're multiplying it by 1.05, that means that your bank is giving you 5% interest. So in 1 year, from the time it took Jimmy to go from his 10-year-old birthday to his 11-year-old birthday, that $1,000 is now worth 1,000 times some factor. I don't know if it's 4% or 5%, so we're just going to call it X. Plus, his rich uncle gave him another $1,200. And so Jimmy in his bank account doesn't have like a little box that sits there that has this money in it. What he has in the bank really is this polynomial that is 1,000x plus $1,200. When Jimmy turned 12 years old, then that $1,000 has now been in the bank for 2 years. So if it has been given 4% interest, we would take this amount right here, which is what he had when he turned 11, and we'd multiply it times 1.04 again, because it earned 4% twice. And so, but we don't know if it's 1.04 or 1.05. What we do know is that you're multiplying it by it twice, whatever it is. We're calling it x, so it's x squared. Plus that $1,200 now has been in the bank for a year, so that gets multiplied by x, whatever the scale factor is, once, plus his uncle gave him another $800. So now when Jimmy turns 13, his original $1,000 has now been in the bank for 3 years. And so we're multiplying it times x to the third, whatever x happens to be. The 1,200 has been in the bank for 2 years, so we multiply it times x squared. The 800 now has been in the bank for 1 year, so it's just multiplied by x. And then his rich uncle gave him another $1,500. If we take this out one more time, when Jimmy turned 14, in his bank account, he doesn't have a box with his money in it. It's not like he takes his 50-cent piece and 5 years later that same 50-cent piece is still sitting there. What he has in the bank is a polynomial in the bank. And so the polynomial that he has when he turns 14 is 1,000 x to the fourth plus 1,200x squared, or x to the third plus 800x squared plus 1,500x plus 700. And so what we're going to do is take these polynomial functions and first talk about what standard form is. All of these equations are in standard form. And so there are different types of polynomials. Some of the polynomials, like this one, is just a number. Then here we have 2 terms, and the degree is 1 because the highest exponent that you see is x to the first. Then we have 3 terms here, and the degree is 2 because the biggest exponent is a 2. And so the last equation is in standard form also, but it's degree 4, and it has 1, 2, 3, 4, 5 different terms. In standard form, we always have a times x to, let's say it's to the fourth, and then plus b times x to the third. It might be c times x squared, and then d times x, and then plus e. And so in standard form, we're always descending with our exponents. So if it starts with 4, it's 4, 3, 2, 1. Now it doesn't have to start with 4. This is in standard form here, and it starts with 2. But the first exponent, the x squared, is our biggest degree. And then we have all the other degrees after that. And so when we talk about standard form, this is the kind of form that we're talking about. It would just be y equals this, or y equals this, and so on. We're also going to talk about how to classify polynomials by their degree. And so this equation right here is a 4th degree polynomial. It does have other degrees in it, like 1 and 2 and 3, but the biggest degree is a 4. So that's a 4th degree polynomial. This is a third degree polynomial, second degree polynomial, a first degree polynomial. This is like x to the 0. Anything to the 0 power is 1. So this is a 0 degree polynomial. We call that a constant. We're going to get into that here on the next slide. We're also going to classify these polynomials by their number of terms. And so each one of these values here or expressions here is a term. Here we only have one term. But when he turned 11, his polynomial had 2 terms. When he turned 12, his polynomial had 3 terms. By the time he turned 14, there was 1, 2, 3, 4, 5 different terms in his polynomial. So we're going to classify all polynomials in 2 ways. The first way we're going to classify polynomials is by their degree. And so if they don't have a degree, then it's just constants. This might be just like 5, or it might be just 18, or negative 20. There isn't a degree. It's like 5x to the 0. We don't even include that. Those are called constant terms, and these are all constant polynomials. If the degree is 1, then it's linear. So it might look something like this, 5x plus 3. That is a linear polynomial because the degree is 1. This is the same thing as 5x to the first plus 3. And so I'm trying to make that look like a 3, but it's not happening. So this is a linear polynomial. Then we have what we just finished going over in our last unit, our quadratic polynomials. So it might be something like 2x squared plus 3x plus 7. And so these polynomials are called quadratic polynomials, and they're of a degree 2. But then we can have cubic polynomials. If they have something like this, where it's 3x to the third, it might be minus 5x plus 1. And that's a cubic polynomial because the biggest degree is a 3. We can have a quartic polynomial if the biggest degree is a 4, or a quintic polynomial if the biggest degree is a 5. Now this list goes on. If the biggest degree is 6, there's a name for it. But all I want you to know for this unit and this year are those 6 names. Those are things you're going to need to be able to identify. So if we have a 5th degree polynomial, you should be able to call it a quintic polynomial. And so those are things you're going to need to know. We're also going to need to know that if it only has one term in it, we call it a monomial. So if it's just 5x to the third. Okay, now that is cubic because the degree is a 3, but it's a monomial because there's only one term. However, if we have something like this where it's 5x to the third minus 2, now it has 2 terms. The 5x to the third and the negative 2, we call that a binomial. And then anytime it has 3 terms, we call it a trinomial. And so this also goes on, but those are the ones that I'm going to want you to memorize. And so if it is a polynomial that has more than 3 terms, you would just say it's a polynomial with 4 terms, or a polynomial with 5 terms. If it's a degree that's bigger than 5, then we would say it's a 6th degree polynomial, or a 7th degree polynomial. But these terms you should know. And so if I have something like this, let's say it's 5x to the third minus 4x plus 3. Well, then I can classify that 2 ways. It is a cubic because the biggest degree is a 3, and it has 3 terms, so it is a cubic trinomial. So if we go back to the original question with his bank account, this is a constant monomial. This is a linear binomial. Here we have a quadratic trinomial. Here we have a cubic polynomial with 4 terms. So that would be just a cubic polynomial with 4 terms. Here we have a quartic polynomial with 5 terms. So let's move on to the next slide where we have a polynomial. It is not in standard form. We're going to want to write it in standard form. And so we're going to need to add, subtract, multiply, divide, square binomials, all these things that you've done before, but we want to put it in standard form. And so if I'm going to put this in standard form, the first thing that I'm going to need to do is to multiply this quadratic trinomial times this linear binomial. So I'm going to do that by foiling 3 times, or I'm going to take 3x squared times 2x, which is 6x to the third, and then 3x squared times 4 is 12x. Then I'm going to take 2x times 2x, which is 4x squared. Oh, this is x squared here too. 3x squared times 4 is 12x squared. 2x times 2x is 4x squared. 2x times 4 is 8x. Then if I take negative 1 times 2x, that's negative 2x. Negative 1 times positive 4 is negative 4. That's a negative there. And so minus, there's like a minus 1 here, and I'm going to distribute that also here. Minus 1 times 6x to the third is negative 6x to the third, and negative 1 times 6x is negative 6x. And so then I'm just going to simply combine all of my like terms here. I have 6x to the third minus 6x to the third. Those cancel each other out. I have a 12x squared plus a 4x squared. That is 16x squared. Then I have an 8x minus a 2x minus a 6x. So 8x minus 2x is 6x. 6x minus 6x is just 0. So those all cancel themselves out. And then I have the minus 4. So my final answer in standard form is 16x squared minus 4. And if I classify it, it is a quadratic because the degree is 2. So it's quadratic. And then it also has two terms. So I would call it a quadratic binomial. The next thing that we're going to want to do is to find a polynomial that is a good model for a situation. And so here it says to find a cubic function to model the data below. And so here we have in 1940, the average amount of Social Security that people received was $22.71. 1950, it jumped up to $29.03. And you can see the amount of Social Security that people receive has really increased rapidly from 1940 to 1999, and they want us to find a model and then predict the amount of Social Security that somebody would receive in 2005. So we're going to need our calculators to do this. And so first thing I'm going to do is take my calculator out and go to Stat, and I'm going to edit, and I want to put these in a list. Now it says to let the x values be years after 1940. So 1940 I plugged in the year 0, 1950 was 10, 1960 was 20, and so on. So these are my x values here, my list 1, and then my y values are the $22.71. You can see, boy, it really went up quickly, starting in 1970 and going up through 1999. And so we plug those numbers into our calculator. And then we're going to want to graph these numbers into our calculator. Right now, if we press graph, they're not there. So we're going to go to our second y equals, and we're going to turn the plot on. And I want my x values to come from list 1, my y values to come from list 2, and I'm going to make them be plus signs. I'm going to change my window here. So I made my x values go from negative 10 to 60 because my x values go up to, I think, 59. My scale is 10. My y minimum, I put negative 100, but it has to go up to at least 757. So I made it go from negative 100 to positive 800, and I'm making the scale 100. And now when I graph that, you can see the points that are on here. You can see the increase here of the Social Security benefits. And then what we want to do is come up with a line of best fit. So to make my line of best fit, I'm going to go back to Stat. I'm going to move over to Calculate. I'm going to move down to a cubic regression line because it's once a cubic function here. And so I'm going to press Enter. And just like before, I'm going to go second list 1, comma, second list 2. That's where my y values are going to be located, comma. And I'm going to go to vars, y vars, and it is a function. And I'm going to put it in for y1. So now when I press Enter, I have a cubic function. It's ax to the third plus bx squared plus cx plus d. Those are my a, b, and c and d values. It's typed in my y equals equation for me, and the graph looks like this. You can see it kind of models it pretty closely. It's a cubic function. And then, so I'm going to go to second, and I'm going to set my table. I want my table to start at, let's say, 60, because in 2055 would be 65 years after 1940. And now I'm going to go to second and table, and you can see in 65 years after 1940, the average Social Security would be $955.82. So I'd like to see if you can do this problem the same way before tomorrow.